Softmax function. The softmax function converts a vector of raw scores, that is logits, into a probability distribution. That is, each element in the output vector will be in the range 0 to 1 and the sum of all elements will be 1. So this is why it is a probability distribution. If there are 5 different values in the output vector, if you sum all those 5 values, you will get 1 and each of those 5 values in the range 0 to 1. So because of this, you can interpret it as a probability distribution. And where is this useful? This is useful, that is the softmax function is useful in multi-class classification tasks because you can see it as the probability of the output belonging to each class. Okay. So you may feel like this is very similar to the sigmoid function that we learned, the softmax function, because sigmoid also did something very similar. It used to take something from the real line, that is from real numbers, and it used to map it to the range 0 to 1, that is in order to interpret as probabilities. The difference is sigmoid had single output, but the softmax function works on a vector output, that is you have multiple dimensions. So while you used sigmoid function for two-class classification, softmax can be used for multi-class classification. So this is the difference. So one general use of the softmax function, it is in the neural networks where you use it in the final activation layer. So you have some neural network. This is the, let's say, penultimate layer. And when you take it to the final activation layer, you use a softmax function. Why do you do that? Let us say you are doing some sort of classification with this neural network. Softmax function will help you to interpret it as probabilities. So the values will be something like 0.2, let's say 0.4, 0.1 and 0.3. Let us say these are the values. So you can interpret these as probabilities where let us say class 2 is having the highest probability. The other classes are having comparatively lower probabilities. So using this you can do classification. This is where softmax function is used. Let us now understand it mathematically. The softmax function, its equation, what is the significance of each term in that equation? Let us see. Let us say you have an input vector x, which is a k-dimensional vector. So x can be written as having k dimensions, x1, x2, x3 up to xk. So this is not k different inputs. Instead, this is a single k dimensional input. So this is one input vector that you got, which is of k dimensions. How will you find the softmax? Softmax you have to find for each dimension. So let us say for the ith dimension, it will be e power xi divided by summation over all the dimensions j equal to 1 to k e power xj. Okay, this is your softmax function. So the softmax function you have to compute for each of the dimension because then you can interpret it as the probability of it belonging to each class. What are the specialities of this softmax function? The first speciality is that in the output, all values are non-negative. All the output values are non-negative because if you have negative values, you can never consider it as a probability. The second property is that every value is in the range 0 to 1. Whatever you get from this function, it will be in the range 0 to 1. And the third property is that the summation of all the values will be 1. That is all the SIs if you sum S1 plus, S2 plus, S3 plus up to SK. If you do, you will get 1. So these are the three major properties of the softmax function. The next step is, let us understand each part of this equation and what it means. Okay. So you can already note that each element of the input vector x1, x2, x3, etc. we are exponentiating all those in the formula. So you note these things. One is that you are taking the exponent of each of those values. And the second thing that you have to note is that you're normalizing everything. That is why you have this in the denominator. You're summing up over all the values in the denominator because you're trying to normalize. So these are two things what you need to conceptually understand in softmax. Why are you doing these two operations? So let us understand this. Why do you have this particular numerator? And why do you have this particular denominator? What is the significance of these things? So the first thing, why are you taking the exponent? Why are you taking the exponent? Why? There are two reasons. The first thing is that when you take the exponent of any value, you can always get a positive value. That is, if you take e power x, irrespective of what the value of x is, you will always get a positive value. So while discussing the properties, we discussed that we should always have only positive values. So when you take the exponent, you will always have a positive value. This is the first property. That is, you will always have positive value. And what is the second reason for using the exponent? This is even more important. That is, let us say your dimension outputs in your multiple dimensions are, let's say, x1, x2, x3, etc. And these may be, one may be larger than the other, but this may not differ by a huge difference. So let us say they are in some sort of a difference, but not in huge. Let us say x2's value is 5, x1's value is 3, and x3's value is, let's say, 7. So clearly x3 is a larger value, but the difference is not very high. They are in some sort of a near interval. When you take the exponent, what happens is, if the one value, let us say, is larger than all others, when you take the exponent, it will become way larger than all other values. So the difference between your different values, that will get magnified when you take exponent. So this is one point. And the second point is, when you take exponent, if some value is smaller than the other value, that will again become very small. So the difference between your values, between your multiple outputs, they will be magnified by exponent. Why do you need this? You need this magnification because that will help you in clearly deciding which is the class to be classified it into. So you want one particular class to be seen with a very large value compared to all others. So whatever be the difference in values, that will be magnified by taking the exponent. So these are the two reasons why you are having this numerator. In the numerator, you can see you are taking e power x. So the reason for taking that exponent, that is, one is for having positive values, and second thing is for magnifying the difference between the outputs. And the second thing, why do you have this denominator? Why are you trying to, what is this denominator doing? It is trying to normalize the value. That is, if you are having values, let us say 2, 3, and 4, what is the denominator doing? It is trying to normalize. That is, you'll do 2 divided by, what is 2 plus 3 plus 4? It is 9. So you would do 2 by 9, 3 by 9, 4 by 9. Considering e power x value is this. So, okay. So what will this do? This is normalization. You are taking the sum to 1. That is, you are normalizing each of the values. Why do you do normalization? The only reason is you want the sum to be 1. So that is when you can interpret it as probabilities. So this is the reason why you have these specific numerator and denominator. The reason you're taking exponent, we explained. And then the reason you're taking sum of all in the denominator, that also we've explained. One more thing before we conclude this lecture is that from machine learning perspective, one operation that you always want to see while you're considering it for any activation function or so is how to take the derivative. Okay, derivative is very important because you will have to see the gradients, and whenever you are using an activation function, it's very important to see how easy is it to calculate the derivative and what exactly is the derivative. So here let us see what is the derivative of a sigmoid function. Okay, we are softmax function. Sigmoid we had already seen in the previous lecture. So if you're taking the derivative, as we already told, you have to take derivative with respect to each of the values. So let us say I want to, I have an output, let us say x is equal to x1, x2, x3 up to, let us say, xk. This is my input vector. If I'm taking the derivative, I have a softmax s, let us say, and this s is for each dimension. There will be s1, s2, s3 up to sk. Okay, this is the softmax corresponding to each dimension. What will the derivative be? Let us say del by del xj of si. Okay, of each dimension you're trying to take derivative with respect to some dimension. If you're trying to take this derivative, you will get softmax of I into del ij. So this is, we'll explain what this term is, okay? Minus Sj. This is the derivative of the softmax. So here this S refers to the softmax of the ith dimension or the jth dimension. And what is this term? This is important here. Delta ij, this term will be 1 if I is equal to j. And this will be 0 if I is not equal to j. So in case of I is equal to j, you will have this value as 1 and your derivative will be Si into 1 minus Sj. Okay. And in case I is not equal to j, then your derivative will be Si into minus Sj. So that will be minus Si Sj. Okay. This is, so you will have two different derivative depending on whether I equal to j or I not equal to j. In order to handle this scenario, we included this value delta ij, which will change values between 0 and 1 depending on whether I is equal to j or I not equal to j. And you call this as Kronecker delta. Okay, this is called as Kronecker delta. This is the derivative of softmax. And one more thing is that if you are calculating this in matrix form, then this can be written as, how do you calculate in matrix form? You take the whole vector and calculate it once. That is, instead of calculating for each of the SIs, you consider the vector S and you directly convert it into matrix form. So in that case, if you are taking the derivative, what will happen? Del by del x of the sigmoid. This will be the diagonal of S, diagonal matrix S minus SS transpose. This will be your derivative. So how do you interpret this? Diagonal S is, you have k different values of S. So you will write it in the diagonal matrix. That is, it will be S1, S2, S3 and all other values will be zeros. Okay, that is the diagonal matrix into SS transpose. If you do this, you get the derivative in matrix form.